Welcome back to linear algebra. Let's jump in. What an intro. Okay. Of what matrix is a to the power, or to a to the negative n, to the power negative n? A to the negative n power, I think, is how you say it. The inverse, it's the inverse of a to the power, a to the second power. Not second, I meant nth power. Oh, I missed it, but I knew what I did. I just misspoke. Yeah, I'm gonna say good. I know the answer to that. Golly, dude. Golly. All right, I'm gonna grade what I did yesterday, then I'll be back and go from there. All right, so I didn't actually finish any problems yesterday. I was just working on this theorem, so I'm gonna continue working on this theorem, and then I'll continue doing more problems if I have time after that. All right, guys, we finished the theorem. So it's very clunky. This one may or may not be valid. It probably is valid, but it's just really not rigorous or elegant at all. But if A is defined, then for K, the product of K, the scalar K times A, or the transpose of that, the transpose of the resulting matrix of K times A, we start with K times A because of the order of operations. K is a scalar and A is a matrix given, so K times A is multiplying each entry of A by K, so every entry can be represented as K times A sub ij. If K times A is a matrix represented by entries of K times A sub ij, then the transpose of K times A is a matrix represented by entries of K times A sub, should say sub ji. If we evaluate K times the transpose of A, we start with the transpose of A because of the order operations. If A is a matrix represented by entries A sub ij, then the transpose of A is a matrix represented by entries A sub ji. If the transpose of A is a matrix represented by entries A sub ji, then K times the transpose of A is a matrix represented by entries K times A sub ij. That should say ji again. Why did I just that would, maybe it's valid now. It was completely invalid before. If K times the transpose of K times A is a matrix represented by entries K times A sub ji, and K times the transpose of A is a matrix represented by entries of K sub A sub K times A sub A ji, then K, or the transpose of K times A equals K times the transpose of A. All right, that was a lot of words for such a simple proof. All right, then we did a bunch of true or falses. First one was asking if you can get A and if you can get B from A using elementary row operations, or if you can get B from A, if B and A are row equivalent and B and C are row equivalent, are A and C row equivalent? Yes, because you can go from A to B using elementary row operations, and then when you're at B, you can go to B to C, so you can go from A to C. True. So this one is, what is this question? If you can't get an inverse from one, then you, okay, so it was asking if you have a matrix that's not invertible. If you have a matrix in which you interchange two rows, is that matrix possibly invertible? No, because you get an inverse using you get an inverse from the original matrix using a sequence of elementary row operations. So doing an elementary row operation on a non-invertible matrix is not going to make it invertible. If you have a matrix that's not invertible, then no other matrices that are row equivalent are going to be invertible either. And then this last one, I'm not sure about actually. It's saying what is it? An expression of an invertible matrix A as a product of elementary matrices is unique. So you got this sequence of elementary matrices, and it's an expression of the invertible matrix A. Is it unique? What does unique mean? I don't know what unique means here. If it means that there's only one sequence or expression of elementary matrices to represent A, then I say no, it's not unique, because you can potentially do different elementary row operations in different orders, which means you'll have a different sequence of elementary matrices to represent A. So that's it for today. Talk to you tomorrow. See ya.